I apologize. Okay, we are going to be looking at some of the questions now from the homework, because you know that sometimes they phrase them in their own unique way. So I'm condensing, this is version question 1, and they'll do a whole load of intro that really is there, but you could almost ignore it. The gist of it is that you're drawing 2 cards from a deck of cards and you're not replacing it. And they mention that one event is independent of the other, which you could almost say all of the questions have that sense, so don't worry about it. Now, it's not replacement, it's a pack of 52, and the first card is going to be a king, and the second card is not going to be a king. Now, we know that when it's 2 cards or 2 anything, don't you multiply together? Now, the first card is a king. We did something very similar to that yesterday. Isn't that 4 out of 52? Okay, now, that card is not being replaced. That means that when you come to do the second card, there's only 51. Now, you have to be a little bit careful in the counting here. Of those 51 cards, how many of them are not a king? Now, remember, there's a king gone. So how many
is
are
it
not
3
a king?
or not?
That's how many kings there are. So use that number
You
in
would
reverse.
have to take 51 minus
48.
Yeah, what you were about to say, Cheyenne. Yeah, take it away from 51, 48. Does that make sense? 4 kings out of 52, and then 48 cards that are not kings out of 51. You see, that's a little, you know, they like putting little twists on things, you know. So that was a twist. So on this one, they want all the answers to be decimal, so I'm not going to worry even about attempting fractions. Do you notice I put little brackets around everybody to make sure the calculator does them in the right order? And the answer to how many decimals? To 4 decimal places is 0.0724, and you're finished. So far, so good. Right. The next question, I'll just kind of read it out. It'll save me jumping back and forward. A woman plans to have 2 children, and the probability that she's going to have a boy is about 0.526. And then it goes on and says that they're independent and without replacement or blah, blah, blah. What's the probability she'll have 1 child of each sex? So that is actually made up of 2 separate events. We did do one kind of like this last time, right? Now, this here is it technically when you do babies, isn't it with the replacement? In other words, one probability doesn't affect the other. So in this case here, what we're looking at is the probability of a boy times the probability of a girl. And so a boy is 0.526. So how much is the probability of getting a girl then?
0.474.
Right, whatever's left from 1, agreed? 0.474. So I'll go to the calculator and I'll do 0.526 times 0.474. And they want the answer to 4 decimal places, so 0.2493. Now, if you do a girl then a boy, couldn't you probably save yourself a lot of work? Because isn't it just going to be 0.471 times 0.562? So really, isn't it just going to be the same answer? You know, one of them's like, you know, A times B and the other's times B times A. But if you put the numbers in, 0.474 times 0.526 is that. And so the answer I'm looking for is the addition of those 2, right? Because there's 2 ways it could happen. That's the probability of the first way happening. This is the probability of the opposite of that happening. And you get 6 and 8 and 9 and a 5. And so the answer is, well, I can't count, sorry, it's a 4. And the answer is 0.4986. Can we do this for 3 girls? Probability of getting you know, 4 girls, 2 boys, whatever you want. You could do them as well. Now, the next question is to do with a raffle. This is question 4. A raffle is held in a club in which 7 of the 41 members have bought a raffle ticket, are good friends. Okay. The club they're good friends of the club president, and the club president draws 2 winners. Okay, so what we got is 14 people. Right. Everybody takes part. There are 7, I'll call them friends. Question A says you pick 2 people to win. And they use the word with replacement. So there's 2 prizes, right? One's a bottle of whiskey and the other's a bunch of flowers, right? Whatever the 2 presents are. When you do with replacement, doesn't that mean one person could win both? Right? With replacement. So you say, and the whiskey is George, and everybody claps and you give George a bottle of whiskey. And then you go, and the winner is, would you believe it? It's George again, right? And he gets the second one. That's what with replacement looks like. So we want to know then, what's the probability? Yes. What's wrong? Are we good? Okay. So we are looking at what is the probability that 2 friends, right, win? Right. So friends of the guy. So since it is with replacement, a lot of background here. I'm going to close that off. No, I'm not. I'm hitting the wrong button.
Okay. That didn't feel good.
There we go. Are we all mute? I think. Right. So 2 friends win with replacement. So it's probability that a friend wins times the probability of a friend winning.
Mr. Robertson,
Yes.
I can't see the whiteboard.
You know, that might be helpful. There we go. So the probability 2 friends can win. Since it's with replacement, don't we just need to find a probability and they don't change? So what's the chance that a friend wins? Well, 7 out of 14. And what's the chance that a friend wins the second prize? Since everybody could win, it's that guy. And that's going to be, oh, I don't need that one. In my case, that's going to be 0.25. Now, what happens if you do the same thing? The probability that 2 people win, only this time without replacement. So that means if you win a prize, you can't be picked again. So that's going to be, so the probability that 2 friends wins, that's going to be 2 things multiplied. The first time, isn't it going to be 7 friends out of 14? Now, what is going to be the next one? Well, that friend has won a prize. So he's left the building. Just like the card game, right? That king's been used up, whatever. There's only 13 people left. How many of them are friends?
6.
First 6, right? 7 friends, but you won it. So one of them has to leave, right? Now you put those 2 guys together. The answer is going to be a little bit less. Into 2 decimal places, it's going to be that less. Does that make sense that the chances that 2 friends both win is going to be smaller when When one person wins, they can't win again. As opposed to you can win all the prizes theoretically. Kind of makes sense, doesn't it? Oh, they didn't do this one, but imagine that there were 3 prizes. If I was doing this one, wouldn't the calculation just be multiply by another 7/14? If it was 3 people, same story, it would be 7/14 times 6/13. But what would the last fraction be? The chance that a friend won the 3rd prize as well. What would this fraction be when you do without replacement?
Five twelfths.
Are you comfortable with that? A friend won. Now there's only 13 people left. 6 are friends, so 6 out of 13. A friend wins again. There's only 12 people left, but only 5 of them are friends, right? Used up, used up. The next one would be 4/11ths, wouldn't it? And the next one would be 3/10ths, and so on. And the next one is even more strangely worded. It's going to be with replacement again. And what is the probability that neither winner is a friend? So it's 2 people, 2 winners, 2 people being picked with replacement, and neither winner is a friend. Well, wouldn't that be not a friend and not a friend? Now, unfortunately, in my combination, 7 out of 14 are friends, but doesn't that also mean 7 out of 14 are not friends? But can you imagine it was, 0.3 were friends and 0.7 weren't. So these 2 guys are simply just going to be multiplied together. And as a fraction, 7 people out of 14 are not friends. And unfortunately, I wish I had got a better combination of numbers, but it is what it is. And the other one would be the same story, and it would look very similar. So let me pretend I've got another version of that. Let's have a group where there's 3 women and there's 7 men, right? And they're going to pick 2 winners. Now I would like to know what's the probability that neither of the winners is a man. That would be the equivalent of that story, right? Now it is with replacement. So neither is a man. Isn't that another way of saying it was 2 women? And the probability of a woman times the probability of a woman, I can do that because it's with replacement, in which case the probabilities do not change. And to get a woman, it would be 3 out of 10 in both cases. And that would be 0.09. Now, if I do the same story with one change, without replacement, the chances that neither of the women is the winners was a man becomes woman again. The first one, there are 3 out of 10, right? There's 3 women out of a total of 10. But once the first person, in this case is a woman, doesn't that mean there's only 9 people to get the second prize? And how many of those are also women?
2.
2. Are we getting used to the using up one of the numbers in the top and the using up one of the numbers in the bottom? If you multiply that horrible mess together, you get to 2 decimal places at least 0.07. Any questions before we look at some other situations, a new situation?
Yeah, I need help with number 2, and for number 3,
Okay,
Right.
well, 2 is good because 2 is where I'm going next. So let's start with 2.
just the table is, I don't
Yeah.
get it.
Right. In question 2 then, I'll just show you the table rather than jumping back and forward. At least my version of the table looks something like this. And essentially, it's a bigger table than I need, but whatever. So, child 1, female. Child 1 was a male. Child 2, don't have room, so I'll put F for female. And child 2, male. And 28, 29, 31, and 33, which adds up to a grand total of, oops, over here, adds up to a grand total of 121. So what has happened here is someone's collected data on 121 families with 2 children. And 28 of them, the first child was a female and the second child was a female. So 28 of them, both were girls. That 33 then would be child 1 was a male, child 2 was a male. So that represents 33 families had both males. Do you see? For instance, that 29, doesn't that mean the first child was a boy, a girl, and the second was a boy? And this one here, first child was a male, second child was a female. So you can imagine that's all the things that you could get, right? I get a boy and then a boy, or a boy and a girl, I get a girl and a boy, or I get a girl and a girl, right? The 4 combinations that are out there. Now from this table, we're now going to calculate some probabilities that if I choose one person from this sample of 121, we're being asked to, good grief.
Hi.
Wow. We are being asked to find the probability, and I had to do a double take on this. Did not have 2 children who were both males.
Yeah, what does that even mean? Did not have 2 children, but they were both males? How do you have 2 males with not 2 children?
Well, you got to interpret what they're trying to say here. So I'm going to put down every combination and see which one of those fits that description. If you look at this, forget the does not have part. 2 children who were both males, are both males would be that one. Would you agree? 2 children who were both males. Wouldn't that be that event? Now, what does it mean when you say did not have? Well, doesn't that mean the exact opposite of that? So isn't that a very, very roundabout way of saying it was these 3 things? You see how I did that? I ignored the did not have. It, you know, in English, when you do those double negatives, it gets really messy in your brain to keep track of. If I said to you, I'm not going to do my homework, what have I just said?
You're
Anybody?
gonna do it.
I'm going to do it. You see how weird it is when you start doing negatives of things that are not already, yeah, we don't like that.
So you would do the 3 out of the total?
Yeah, now it wouldn't be 3 out of 4. We would get the people that we're talking about here. So let's see, a male and then a female. So male and then a female would be 31, right? So that would be 31 people. A female and then a male would be that one. So that one would be 29. And a female and another female would be that one. It would be 28. So my probability would be out of the 121 people, couldn't I add all these together? So that would be 31, 29, and 28, which is 70, which is 98 out of 121. Or couldn't I get the exact same answer by just taking 121 and taking away the 33 who are males? Do you see it ends up being the same result? Now, it depends on how your brain works. Does adding up the 3 people that represent the red circles and getting 98, does that click in your brain better than saying, well, the people who are not males are the rest, right? So take away 33 and you get this guy. The answer to that as a decimal is 0.73. Does that question make more sense now? God forbid they stuck another negative in front of that. What's the probability that they didn't have not having 2 children who were both not males? I mean, you can go crazy with the knots, couldn't you? Thank goodness they didn't do that. That was bad enough. Now, they had a second part to that, which is whether the following statement is true. So the guy that we would calculate, maybe it was, in this case, 98 of 121. Is that a statistic or is a proportion? Is it true? Well, yeah. Suppose I went and told you that the probability that they were both females was 28 out of 121. Would that be correct? The probability that you chose someone and they were both females, is that 28 out of 121? Now look at your table, does that work? Yes or no?
Yes.
Yeah, there's the right number. If I'd said to you that the probability of getting 2 females was 33 out of 121, wouldn't you say, no, that's not right? This one is true. This one is false. In fact, isn't that the probability of getting 2 males? It's not the probability of getting 2 females. So that was question 2.
Okay, now for the question 3,
I
did the probability of the boy times the probability of the girl, and then I added them, but it says I got it wrong.
Well, did you do it the way that we said? Because it's 2 children. So
Yeah.
what you needed to do there was actually
Did you
find,
double? I made the same mistake. Did you double check what your probability for the boy is? Is it the exact one that he did? Because mine was different than what his was.
No, yeah, it's a 0.534. So I
okay,
minus that from 1, which is 0.466. So I times
Right.
that, which is 0.2488. And I added those together, which is 0.4976, but that said it's wrong.
okay, let's check yours out. So you had the probability of a boy, which was in your case 0. What again?
534.
Right, and if you take that away, you'll get the girl then. So if you take that away from 1, did you get 0.466?
Correct.
Okay, so you're being asked one of each. So if you do the probability of a boy and a girl in this case, you would be going 0.534 times 0.466. And they want the answer to 4 decimal places, so I'm going to round that off when I'm finished. 0.534 times 0.466 And the answer I've got here is 0.2488. You agree?
Correct.
And the other one you're going to get is 0.2488 as well, because when you switch them around, you get the same guy, right? So I don't need to write it down. So according to you, you're going to get 6994. Is that what you got?
No, I got 0.4976.
Well, you did. Agreed?
Because it's not 9, because 8.
No,
Yeah.
no, you're right. It's 7.
Yeah.
So 4976.
Yeah,
Now,
and it says I'm wrong.
no, well, yes and no. Bad answer. If I write down the other 2 digits, you get that. And then when you round that answer off, you see how the last digit becomes a 7. And so I guess the moral of that story is, and I almost get caught out as well, is shouldn't you only round off the final answer to 4 decimal places, but keep everything else to as many decimal places as you need?
Well, I don't get, why did you do that? Because it's,
Well, it's just a rounding off issue, right? If you leave these numbers to a lot more accuracy and add that, and then this is the guy that you round off, to see how this fellow would round up. And you would then get an answer very, very similar to the one you got, but just rounded off a little bit differently. So that you weren't doing it wrong. You were doing the right calculation based on the numbers you gave me, at least. That worked.
sure did.
Moral of that story is WebAssign can be a pain in the butt, so be accurate. Because you were doing it perfectly fine. Question 5 is a very big table. So here we go. And we're going to be looking at creating this table. So your job is actually to fill in, what's that going to be? 9 missing numbers. Oh, there's a lot of missing numbers. And so you have junior, you have senior, and then you have the total. And then you have students that do calc, students who don't do calc, and then you have a total. And all of these are going to be done from some information. And so here is what they told me in my question. Half of the senior class and 10% of the junior class take calc. And in this question, there are 300 students. So we have to figure out how to put numbers here, 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 and then you can do the totals after that. So what do I know? Half of the senior take calculus, right? Oh, forgot to tell you. Half.
First sentence says that half of the students are in each grade.
Yeah, I missed that. So half the students are in each grade as well, right? So here goes, 300 students. Half of them are going to be juniors, right? And half of them are seniors. Are you comfortable about those 2 numbers? Now, of the seniors, half of them took calculus. So there's 150 seniors. Half of them took calculus, which is 75. How many didn't take calculus?
75.
75. Now, in the juniors, only 10% take calculus. So how many juniors took calculus? Right, there are 150 juniors, 10% take calculus. How many are there?
15.
And would you agree that leaves 135 for the rest? So far, so good. Now, totals, if you add these up, 90. If you add these up, 210. And if you add those two totals, it should be the same as these two, and they are, so I know I've done it right. And that's the table filled in. So there wasn't really any probability in this question, wasn't it? Just here's some information. Can you fill in, the details using these 3 facts? That one is to kind of lead you up to question 6. Suppose a magnet high school has 11 or 12 students, right? And it's the same as before, right? Half in each grade. So half are in junior, right? Half are seniors. %60 of the seniors take calculus. And again, 10% of the juniors, at least in my question, take calculus. Suppose a calculus student is randomly selected to accompany a math teacher to a conference. What's the probability that that student is a junior? So we are being asked to find what's the probability that the student is a junior given that they take calculus. And that is not an easy question. It's a conditional probability. And this table over here was actually to help us. So I'm going to do another version of that same table. So here are the ones that take calculus. Here are the ones who don't take calculus. Here are the juniors. Here are the seniors. Oops. Total's going to go here, maybe. Total's going to go here. But there's one thing missing here, but I'm going to make a little assumption here because it works. I'm going to assume, to make my life easy, that there's exactly 100 students in this very small place. Now, there's 100 students. Doesn't that mean 50 of them are juniors and 50 of them are seniors? Now you might say, well, why'd you pick 100? Actually, it doesn't matter. Do you know I could pick 20,000 or 500 and the math ends up cancelling down to the same answer. So it really doesn't matter. Now, 100's a nice number as well. That's another reason to pick it. If you look at the juniors, 10% took calculus. So doesn't that make it 5 juniors and 45 here? And 60% of the seniors, and I believe that ends up being 30 and 20. And that makes this total 35, and that makes this total 65. Are you comfortable about how I created this table? So far, so good, right? Now, when you have a conditional probability, the probability of picking a junior given that it's calculus, the bottom number should only be people who take calculus, right? Because you know that's true. In my table then, isn't it 35 people who take calculus in total, right? So that means my bottom number is 35. Now, only for those students who take calculus, only those students, how many of them are juniors?
5.
So there's your probability, which simplifies down to 1/7, which is the right answer. So if you get one of these questions where there is a missing total, like I don't know how many people you're talking about, it's only percentages, you can create this table. I think 100 works out really well, but even if the numbers don't make a lot of sense, you know, like you may get 5.1 people, it still works even in those situations. Right?
I don't know how to find 70% of 50.
Oh, well, if you only find 70% of 50, on a calculator, 0.7 is the decimal version of it, times 50, that would be 35 people. So that's how you would find it.
Better, thank you.
Are we good? Right. The next thing that we're going to do, and I think I've just got enough time, and we'll continue this tomorrow. So it means that as far as you're concerned, that the midterm finishes on chapter 7. So I'm going to adjust the homework accordingly. We are going to look at what are called a probability tree. Probability trees are used when you have got complicated information that involves 2 steps typically. Right? So imagine that we do, as our example here, a bag with 3 blue, I guess I'll make them blue, 3 blue beads, and 7 green ones. And we are going to do without replacement. Right? So every time you use something up. And we are going to look at picking 3 beads out the bag. And I'm going to look at how you construct a probability tree for this story. So you kind of turn the tree on its side and you do your first pick. Now your first pick could be a blue or it could be a green. And what's the chances that your first pick is a blue? Well, there's 3 blue out of 10. And what's the chance that it's a green? There'd be 7 out of 10. So that's how you get the first branch, right? 3 out of 10, 7 out of 10. Then it gets a bit messier. Let's choose a second bead. It could be a blue bead. It could be a green bead. Now, the way this tree works is you have to find where it came from. In this branch here, hasn't a blue bead already happened? So what's the chance that the next bead is also going to be a blue? Well, there's only 9 beads left, and isn't there only 2 blue ones in there? So this one becomes 2 9ths. So what's the chance that the second one's going to be a green bead? Right, the first one's blue, 2 9ths that the next one's also a blue, but what's the chance that the second one ends up being a green instead?
7 9ths.
Right. Have you noticed that the 2 guys always add up to 1? So if you know what 1 is, whatever's left is the other. Now, if we go the other route, right? The first one was a green. Well, the chances that the second one is a green is 6 9ths. Agreed, 1 of the greens get used up. And the blue is the rest, 3 9ths. And then you do it one last time. And you normally only do these things to 3 branches because they're really ridiculous if you try and do it for anything more. And if I'd planned ahead, I would have gave myself more room. And I'm going to put these ones in red just to help them stick out. Now, let's look at this last bead, this blue one here that I'm pointing at. How did that happen? A blue bead the first time, a blue bead the second time. What's the chance that the third one is a blue? How many beads are going to be in the bag and how many are blue? That's basically how you find out.
Right?
What would 1/8? Agreed? Now, what does that make the other one? Because can't you just use the fact they always add up to 1? So if that's 1/8, what does this one end up being?
7/8.
7/8. So as long as you find one, you can get the other. Right. Now, the next one is getting kind of messy. 2 beads have happened, but one was blue and one was green. You see that? A blue and then a green. So I know I've got 8 beads left, but how many of those 8 are blue in this story?
2.
Great. And the other 6/8. Now, if you move on to the third branch, a green and a blue have happened. Would you agree that there's 2 out of 8 and 6 out of 8? Again, I'm just speeding that one up. And for the last one, 2 greens have happened, right? A green and a green. That's going to make a difference, isn't it? Each event has an effect on the probability. So there's only 8 beads left. How many of those are blue? If it was a green and then a green. Out of the 8 that are left, how many are blue?
3.
Okay. Which makes that 5/8. And what we now do is you multiply the pathway. So see to get to that one, it was a 3/10, a 2/9, and a 1/8. So you would go 3/10 times 2/9 times 1/8, so you get the answer. If you wanted this one, since I don't have time to do all of them, this one here, it would be a green, a blue, and a blue, and you would multiply the pathway 7/10 times 3/9 times 2/8, and you get the answer. So whatever that came to, that's the probability that the first one was a green, the second one was a blue, and the third one was a blue. Now, once you've done that to all of these, right, every single one of these, you multiply the pathway. So these are massively big questions. Once you've done that, you now know every single thing that could happen in a 3-bead story, right? So I'll know all these probabilities. So for instance, if I wanted to know what's the chance that all 3 were blue, it would be this one, wouldn't it? And that answer would be, let's turn it into a decimal, 3/10. Actually, I might do this as a fraction. I think it will work. It's 3/10 times 2/9 times 1/8. And let's see what that looks like as a fraction. So the chances that every single one of them was a blue bead would be 120. But I can also do complicated probabilities as well. I can, for instance, tell you what's the chances that you get 2 blue and 1 green in any order. Right, 2 blue and 1 green would be, that event would be 2 blue and a green. That event would be 2 blue and a green. Any others?